Okay, so chapter 8 is all about integration. Remember, with derivatives, we can use the chain rule, we can use the product rule, we can use the quotient rule. But with integrals, we can't use any of those rules. So we end up having a lot of different types of integrals that we evaluate in a lot of different types of ways. So we're going to look at a special case in 8.2. Now we're skipping over 8.1 because 8.1 is sort of a summary of the types of integrations that we've had so far. So feel free to review 8.1 if you wish, but there's no new information there. But in 8.2, we're going to look at a different type of substitution called integration by parts. So the first thing I want to do is show you where the formula comes from. So let's just suppose that we have these two functions with respect to the variable x. We'll have u of x, and we'll look at this function, we'll look at this function v of x. And suppose I take the derivative with respect to x of the product of u times v. Now just to cut down on the amount of writing, I'll leave off the argument there. So I need to use the product rule. And what I'm going to do is I'm going to keep the u times the derivative of v with respect to the variable x. Plus I'm going to keep the v times the derivative of u with the variable x. Okay. So I have this equation, and I'm allowed to integrate both sides of the equation. So on each piece, I'm going to take the integral with respect to x, integral with respect to x, integral with respect to x. So by the first fundamental theorem of calculus, since I'm taking the integral with respect to x on the left-hand side, so I have dx, dx, it all cancels. And this just becomes u times v. Now on the right-hand side, this first integral, the dx's will cancel, and in the second integral, the dx's will cancel. So I'm going to have the integral of u dv plus the integral of v du. So this is not anything that you would be tested on or you need to memorize. I would just really like for you to see where this formula comes from. So this is just an equation. If I were to solve for the integral of u dv by algebra, this is simply going to be equal to u times v minus the integral of v du. Okay? So that's integration by parts, which we have in this boxed area. And what integration by parts allows us to do is to take a product in an integrand and break it up into smaller pieces. So the trick here is deciding what's going to be your u and what's going to be your dv. So usually you want to go ahead and choose a u that simplifies when it's differentiated, so when you take its derivative, and choose a dv that simplifies when it's integrated, if possible. Sometimes that's not possible. So for example 1, I have x times e to the x, which I do not know how to take the integral of because it's a product of two functions of x. So if I take the derivative of x, it's just 1. If I integrate x, it becomes x squared over 2. But notice that whether I differentiate or integrate e to the x, it remains unchanged. So it seems like if I take the derivative of x, it just goes to 1, which is a lot nicer than integrating and getting x squared over 2. So I'm going to let u be the x, and the rest of this integral, I'm going to let this be my dv. Okay? So I'm going to let u equal to x and dv equal to e to the x dx. So this is how I've broken up my integral. Notice that in integration by parts, we need a u, which I have. We need a v. I don't have a v. But if I integrate both sides of the dv equal to e to the x dx, it becomes v. Integration of e to the x dx is just e to the x. Okay. So now I have my v. The only thing left to find is du. And we get du by looking at u equal to x and differentiating both sides to get du equal to dx. Now I have all the pieces. I'm going to just take u times v minus the integral of v du. So this integral becomes u is x times v, which is e to the x, minus the integral of v, which is e to the x, and du is dx. So do you see what we've done? We've broken this up, and now the integral portion we can evaluate. This becomes x e to the x minus e to the x, and then plus our constant c. And I'm done. Okay, so let's try this again with another example. I have x squared and natural log of x. And here I kind of have no choice. I don't know how to take the antiderivative of natural log of x. So natural log of x will have to be my u, because I know how to take its derivative. So that means x squared dx, this is going to be my dv. So I'm going to let u equal natural log of x. So when I take the derivative on both sides, I get du is equal to 1 over x dx. And I'm going to let my dv equal x squared dx. And when I take the antiderivative, it becomes v equal to x cubed over 3. So our integral is equal to uv minus the integral of v du. Okay? So natural log of x times x cubed over 3 minus the integral of x cubed over 3, and our du is 1 over x dx. Okay, so this will simplify. I'm going to rewrite this as, ooh, I like my x cubed in the front. So x cubed over 3 times the natural log of x minus, I'm going to bring out the 1/3, and this is the integral of x squared dx. And that integral I can easily evaluate. So this becomes x cubed over 3 times the natural log of x minus 1/3 times x cubed over 3 plus our constant c. So again, I'm just going to clean this up as x to the 3rd over 3 times the natural log of x minus x cubed over 9 plus my constant c. And I am done. Okay, let's go to some more examples. On the next page, we have x squared and e to the x as our integrand. It's a product. This is real similar to example 1. And I'm going to do the same u and dv. I'm going to let u be the x squared and dv be e to the x dx, because that's much nicer to integrate. And having u be my x squared, that's much easier to take the derivative on both sides of. So my du is going to be 2x dx. And I'm going to let dv equal to e to the x dx. So antiderivative v is equal to e to the x. And then I'm going to take u times v minus the integral of v du, which is going to equal to x squared e to the x minus the integral of, this becomes 2x times e to the x dx. Okay. I have a problem because I still end up with a product of two functions. So what I'm going to do is I'm going to do integration by parts again. Now it's not necessary for me to change the u and the dv because my integral is still in terms of x. So I'm going to put a 1 for the first time I did integration by parts. And now I'm going to put a 2 and do integration by parts again. But first note that this 2 inside the integral, I'm going to bring that out. Okay. So I'm going to have x squared e to the x minus 2. And now I'm going to do the integration by parts again. So I'm going to let u equal x, and then the derivative is du is equal to dx. And I'm going to let dv again be e to the x. So v is equal, or e to the x dx, I apologize. So v is equal to e to the x. And we'll be doing u times v minus integral of v du again inside the bracket. All right, so this becomes x e to the x minus the integral of e to the x dx. And now the integral portion is simple, right? It's just e to the x. All right, so I'm going to go ahead and distribute this -2 here at the same time that I simplify everything, which would give me x squared e to the x minus 2x e to the x. The minus minus turns into a plus 2e to the x, and then add my constant c. Okay. So we can do integration by parts more than once. Just remember to note which is your first time and which is your second time, just notation wise of using integration by parts. So let's look at another example. And then I have a problem with this one. Not just that it's a product of functions, it's that when I integrate e to the x or differentiate e to the x, it remains unchanged. When I integrate or differentiate cosine, it just alternates sine, cosine, sine, cosine. I'll just have a negative or a positive. Okay. So this is a special case where I'm going to let u be e to the x, and I'm actually going to let my dv be the cosine portion, because I want my integral to either have a cosine or a sine in it. And you'll see why in just a little bit. So I'm going to let u equal e to the x. Du is equal to e to the x dx. I'm going to let dv equal to the cosine of x dx. So when I find the antiderivative, v is equal to sine of x. Okay, so again, I'm going to do my u times v minus the integral of v du. And here this integral is going to be equal to e to the x sine of x minus the integral of e to the x sine of x dx. So I do have a problem because I still have a product of two functions of x. So this is my first integration by parts. I'm going to do this again. Oh, I'm going to have to move this over. So my second integration by parts, I'm still going to let u equal e to the x. So my du is equal to e to the x dx. My dv is now going to be sine of x dx. And then my v is going to be antiderivative would be the negative cosine of x. And this becomes e to the x sine of x minus u times v is going to be a negative e to the x cosine of x. So negative e to the x cosine of x minus the integral of negative e to the x cosine of x dx. And I ran out of space. Ooh, just made it. Okay. So something we should note is a lot of negatives are going to cancel. Let me go ahead and just clean this up. I have e to the x sine of x. The negatives will cancel, and this will turn into a plus e to the x cosine of x. Negative, negative, oh, I get a minus. Integral of e to the x cosine of x. So all I was doing is cleaning up all these negatives and getting rid of the bracket. Okay. So what you should note is the integral that I ended up with here is the same integral that I started with, except for I have this minus in front, which is actually what I wanted. Because remember what's on the left-hand side of this equation. This is the integral of e to the x cosine of x dx. Kind of squish that in. So this is an equation. And what I could do is I could add the negative integral from the right to both sides. And these are actually the same integral. So when I add it, I'm going to get 2 of these integrals e to the x cosine of x dx equal to e to the x sine of x plus e to the x cosine of x. And now to solve for my original integral, all I have to do is divide everything by 2 to get the integral of e to the x cosine of x, which is what I started out with, is equal to e to the x sine of x plus e to the x cosine of x all over 2. So it's a roundabout way of evaluating this integral. And the problem is that even when I did integration by parts, I kept ending up with a product of 2 functions. And it wasn't going to go away because the cosine would just alternate between cosine, sine, cosine, sine. So typically what we do is we'll factor out the 1/2 common e to the x and in parentheses write sine of x plus cosine of x. But I actually don't care. You could have stopped at the step before. Just remember you need to add your constant c. So you could have stopped here at this step. I think my math lab will factor. Again, I really don't care which method you use or which answer you write. It's all the same to me. On to the last page, which is where we get to do integration by parts. But this time we're going to do integration by parts with definite integrals. So we're going to have to evaluate these. And it's the same as what we did before. We just have limits of integration. So in example 6, I need to decide what would be my u and what would be my dv. Again, here I have no choice. I don't know how to integrate natural log. So I'm going to let my u equal the natural log of x because I know how to take the derivative of the natural log. It's just 1 over x. So my dv is going to be equal to x dx. So v is equal to x squared over 2 when I take the antiderivative. And now I have my uv minus v du. So my integral is going to be natural log of x times x squared over 2, and I like my x squared in front of my natural log. It's just one of my little things that I need to do. Well, I wonder if I'm going to have space. Okay, and this is limits of integration, right? So we're going to evaluate this piece from e to 1. So I need to put that on there. Minus my integral with my limits of integration, e to 1. Now if I take x squared over 2 times 1 over x, that'll simply be x over 2 dx. So on this first piece, I can go ahead and evaluate that piece, or I can just wait to the end and evaluate the whole thing together. If I do evaluate this first piece, it's going to be e squared over 2 times the natural log of e. Oof, it's going to be hideous. Let me box this. X is e, so I'll get e squared over 2 times the natural log of e. That's actually nice because natural log of e will just be 1. Minus 1/2 times the natural log of 1. Ooh, that's not bad either, because that's just going to be 0. Minus, now with this integral, it's going to be x squared over 2 times the 2. So I end up with x squared over 4. And then I'm going to be evaluating this from e to 1. So in the first part, again, the natural log of e is 1 and the natural log of 1 is 0. So this whole second term is gone. And I just have e squared over 2. Oops, why are you not writing? E squared over 2 minus, why don't I put this all in one piece so it doesn't get confused with the e squared over 2. And that would be e squared over 4 minus 1/4. So combining the e squared, I'm going to end up with e squared over 2 minus e squared over 4 is just e squared over 4. Okay, so that's e squared over 4, and it's minus minus, so plus 1/4. And again, I'm okay if you just leave it that way. You could factor out the 1/4. So typically, again, I'm fine with this. So typically on my math lab, they'll write something in factored form by factoring out the 1/4 and in parentheses have e squared plus 1. Or you can also combine the denominators are the same, so e squared plus 1 over 4. Doesn't matter to me. I'm fine with all of those answers. But what I would like to do is, wow, my page is really crooked, is look at this last integration. Okay. So remember that we didn't know how to integrate the natural log of x. But now we can actually prove this integral, that the natural log of x, the integral of the natural log of x is actually x times natural log of x minus x. And we're going to prove this by using integration by parts. So if I look at the integral of the natural log of x dx, even though it's not there, there's a 1 in front, right? So it's like 1 times the natural log of x dx. So what I'm going to do is I'm going to let my u be the natural log of x, and my dv is going to be 1 dx. Right, so I'm going to do this right underneath. So I'm going to let u equal the natural log of x. So du is equal to 1 over x dx. And I'm going to let dv be 1 dx, which is just dv is equal to dx, which means v is equal to x. So this integral, my u times v is x times the natural log of x minus the integral of x times 1 over x dx. Okay. And that's equal to x natural log of x minus the integral of 1, right? So when I take the integral of 1, that just becomes x, okay? Which gives us the integral of natural log of x is equal to x natural log of x minus x, and then plus our constant c. So now we can use the integration by parts to actually derive the integral of natural log of x. Okay, so this is where we stop.